this lesson, we'll talk about trigonometric functions of any angle. If we place the right-angle triangle in a system of coordinates in such a way that the acute angle theta is in standard position, then the definitions of the six trigonometric functions could be stated as follows. Look at our triangle. The right angle is at the vertex C, and the vertex B is a point on a terminal of the angle theta. So this point can be chosen arbitrary. It could be any point on this ray. It could be here, or there, doesn't matter. What's important is that if we choose a point B, then the projection of B onto the x-axis is actually our vertex C. Its distance from A is exactly x, because this part is the x-coordinate of the point B. Similarly, the height of this triangle is actually y, the second coordinate of the point B. So x and y really represent the length of these two sides of the triangle, and the hypotenuse, the third side, is actually the distance of the point B from the origin, so we can call it r, like a radius. So that's why the system is quite convenient to state definitions of trig functions, because the coordinates of the point that define this angle theta in standard position carry the information about the length of the sides of this right angle triangle. So sine of theta is opposite over hypotenuse, therefore it's y over r, and we have it here, y over r. Cosine of theta, it will be defined as adjacent over hypotenuse, so it's x over r. Tangent of theta, it will be opposite over adjacent, so it's y over x. And those definitions will be very important for you to memorize. So sine is y over r, cosine x over r, and tangent y over x. The first two, remember that we refer to r. R is our hypotenuse. Sine starts with y, cosine with x. Tangent is like ratio between sine and cosine. It's y over x, the top numbers in the same order. And if we have already defined sine, cosine, tangent, it's really easy to define cosecant, secant, and cotangent as just reciprocal of the above. So cosecant is r over y, secant r over x, cotangent x over y. Notice that defining our trig functions in terms of x, y, and r is really useful, because it will allow us to extend this definition to any angle, not only acute. For example, if our terminal is in some other quadrant, even in the third quadrant somewhere there, and the angle is from here to there, we can't really produce any triangle with such large angle. However, we can still make definition of trig functions by choosing a point on the terminal of this angle and referring to the coordinates of this particular point x and y. So we'll have r, x, and y, and we can define any trigonometric function, which we've been not able to do if we look just at the right angle triangle. So this is a great advantage of defining trig functions through x, y, and r. Notice that we have following identities. The first three are directly from definitions of cosecant, secant, and cotangent, because they are defined as reciprocal functions, reciprocal of sine, cosine, and tangent. The last two identities, it's easy to prove from definitions in terms of x, y, and r, and we can do it in a second. Those identities are called ratio identities, just because tangent is a ratio of sine and cosine, cotangent is a reciprocal of it, so it's cosine over sine. Okay, so here we're supposed to prove those ratio identities. Let's start with the first one. If we start with the right-hand side, right side, which is sine theta over cosine theta, since sine is y over r and cosine is x over r, we just need to simplify this complex fraction by changing this main division into multiplication by reciprocal, r over x. And now after reducing r, we have exactly the definition of tangent. So that's proven. The second identity is even easier to prove if we have the first one, because cotangent is the same as 1 over tangent from the definition, therefore is 1 over sine over cosine, so it's really cosine over sine. To find values of the 6 trigonometric functions of any angle theta in standard position, it is enough to know a point xy on the terminal ray of this angle and the Pythagorean relation that r squared is equal x squared plus y squared. If we have the point x and y, it's easy to calculate r, and then using definitions in terms of x, y, and r, we can recover values of any trig functions. So let's try this example. The terminal side of an angle theta in standard position passes through the point -3, -4. Here's our point. Find the values of the 6 trigonometric functions of theta. Well, we have the point. We need to find out the r as well, but as you see on the diagram, this point defines a right angle triangle with one side of length 3, the other 4, therefore the third one must be 5. Okay, so let's list what's x, y, and r, and then we're going to use the definitions of trig functions in terms of x, y, and r. So x was -3, y -4. Radius r is always positive, so it will be plus 5, because that's the distance of the point from 0. So we're ready to list the values of the 6 functions. Sine of our angle theta is y over r, so it's -4/5. Cosine theta is x over r, so it's -3/5. Tangent theta is y over x, so it's two negatives makes it positive 4/3. And then reciprocal functions. So reciprocal of sine is cosecant theta, flip the number -5/4. Reciprocal of cosine is secant theta. Again, flip the number so it's -5/3. And finally, cotangent theta, reciprocal of tangent, so it's 3/4. So you see, as soon as we have the information about x, y, and r, it's really easy to answer the question. Now we are asked to sketch an angle theta in standard position having point -2√3 and 2 on its terminal side. So the y-coordinate of the point is 2. Let's say it's somewhere here. The x-coordinate is negative, so it will be on this side, and it's a little bit longer because it's multiplied by √3. So let's position it somewhere there, approximately. Therefore, our point is here. Okay, so the terminal goes like that. Therefore, our angle theta is from here to there. That's our angle. Then find the values of the first 3 trigonometric functions of the angle theta. Well, in order to do that, it would be nice to list what's x and y. That's what we know. X -2√3, y is 2. But we also need r. How much is r? In this particular situation, I just noticed that this must have something to do with special triangle, because this distance is 2, and that distance is 2√3, which reminds me of a height in equilateral triangle with the side of 4. So if this half a side is 2, that's 2√3 as a height, and this side, whole side, will be 4. So just because of the nature of numbers, we can recover the 4 from special triangle. But generally, if those numbers will be different, not from special triangle, we would just use this Pythagorean equation to find out r. But in our case, we already know the r is 4. So now we're ready to state what's the value of sine theta. That's y over r, so it's 2 over 4, which is 1/2. Cosine theta, which is x over r, so it's -2√3 over 4. We can simplify to -√3 over 2. And tangent theta, that's the same as y over x. so it's 2 over negative 2 root 3. After simplifying, we have negative 1 over root 3. We usually like to rationalize the denominator, so that would be actually negative root 3 over 3. Find the values of the three trigonometric functions for the quadrantal angles. So, as you remember, quadrantal angles are 0, 90, 180, 270. Then they become coterminal with those first four. So here prepare a table of 6 trigonometric functions and we're going to fill it up. It's a good idea to keep in mind the definitions of sine, cosine, tangent, and so on in terms of x, y, and r. Sine is y over r, cosine is x over r, tangent is y over x, and the rest of it will be just reciprocal of the previous three. So if I think about angle 0, just 0, its terminal will be somewhere there. Let's choose a point on this terminal. Let's choose an easy point. For example, a point 1, 0. So now we know the x and the y. Also the r is equal to 1 because this point is at the distance of 1 from the center. So sine theta is y over r, which in our case is 0 over 1, so it's 0. Cosine is x, that means 1 over 1, so it's 1. Tangent is y over x, so it's 0 over 1, which is still 0. And then we want to take reciprocals, but some reciprocals can't be taken. For example, cosecant of 0 degrees or 360 degrees would be the same as 1 over sine of those angles, but 1 over 0 doesn't exist. So cosecant of angles coterminal with 0 doesn't exist, D and E. Secant, reciprocal of cosine, so it's 1. Cotangent, reciprocal of tangent, again, it doesn't exist. Second row, if we think about angle 90, we pick a point on the terminal with coordinates 0, 1, and again r will be 1 as well, and just follow the definitions. Sine is y over r, so it's 1 over 1, so it's 1. Cosine is x over r, so it's 0. Tangent is y over x. Oh, we can't divide by 0, so tangent of 90 degrees doesn't exist. And now take reciprocal. Reciprocal of 1 is 1, reciprocal of 0 doesn't exist, and reciprocal of something that doesn't exist is actually 0. And we can recall the definition of cotangent to confirm that. Cotangent is x over y. So in our case, 0 over 1. So yes, it is 0. Okay, so you see how I've done the first two rows. I will ask you to stop the video and fill up the next two rows. In a second, I will fill it up for you, but maybe you can try on your own first. Okay, to see the angle 180, we can pick a point on the negative part of x-axis, for example, negative 1, 0, and r will be 1 as well. We can pick any point, for example, negative 3, 0, and r3, but that's just easier. So sine of 180 would be y over r, which is 0. Cosine is x over r, so it's negative 1. Tangent is y over x, so it's 0 again. And then if we take reciprocals, reciprocal of the two zeros does not exist. And the reciprocal of negative 1 is still negative 1. Finally, 270. So I will pick a point 0, negative 1 on the terminal of 270 degrees. And r is 1 as well. So again, sine y over r, so it's negative 1. Cosine x over r, so it's 0. Tangent y over 0, oh, it doesn't exist. And reciprocals, reciprocal of negative 1 is negative 1, reciprocal of 0 doesn't exist, and reciprocal of doesn't exist will be 0. So as you see, the quadrantal angles are very special. All the trig functions will have values either 0, 1, or negative 1, or sometimes they do not exist. The next exercise asks us to observe signs of x, y, and r. R is always positive, but the sign of x and y depends on which quadrant is our point in. Okay, so we observe those signs to find signs of trigonometric functions in each quadrant. And here we have a table. If our theta is in quadrant 1, let's find out the sign of sine and cosecant. They are related because if sine is positive, then cosecant, which is reciprocal of sine, will also carry the same sign. And if sine is negative, then cosecant will be negative. Similarly, this pair, cosine and secant, they will have the same sign. And tangent and cotangent, because they are reciprocal to each other, the sign will remain the same. So it's enough to check one function, the other will behave the same way. So let's check sine in first quadrant, y over r. Any point in the first quadrant will have first coordinate positive and second positive. Therefore, basically all functions will be positive because there is not even one negative among the x, y, and r. So everything here is positive. Well, let's look at the second quadrant. Any point chosen in second quadrant will have first coordinate negative and second coordinate positive. Remember, r is always positive. So only those functions that involve x in their definitions will be negative. So x appears in the definition of cosine, so cosine and secant will be negative, and it also appears in definition of tangent, so tangent, cotangent will be negative. Sine and cosecant will be positive, no problem there. If we go to the third quadrant, any point in this quadrant will have first coordinate negative and second coordinate negative. Since sine is y over r, then we have negative over positive, so it is negative in this quadrant. Cosine is x over r, still will become negative. Tangent is y over x, so two negatives makes it positive. And finally, in the fourth quadrant, any point here will have first coordinate positive, second negative. Therefore, only those functions that involve second coordinate in their definition, like sine or tangent and their reciprocals, will be negative. So sine is negative and tangent is negative. Cosine and secant will be positive. Okay, so we built some information about our functions. Obviously, it's not easy to remember all those signs, so that's why we have a word that will help us to memorize the signs in each quadrant for particular functions. This word is cast. Start from C, A, S, T. Cast. Counterclockwise. What does this mean? It means that in the first quadrant, all functions are positive. In the second quadrant, only sine is positive. See, only sine is positive. In the third quadrant, only tangent is positive, as we see in the table. And in the fourth quadrant, only cosine is positive. Obviously, we are referring to the first three functions. We are basically looking at sine, cosine, and tangent, because the other three functions will behave exactly the same as those. So keeping this in mind, cast may help you to decide what is the sign of particular function. Let theta be an angle in standard position. Which quadrant theta could be if we know that sine is positive and tangent is negative? Well, I may ask you to shade particular quadrants that will satisfy each condition. For example, sine is positive in the first and second quadrant, because here all, that means sine as well, and over there sine. So what we can do is shade the first and second quadrant. These two quadrants satisfy the first condition, sine is positive. Now for tangent to be negative, first let's recall when tangent is positive. It is in the first and the third quadrant, therefore negative is in the second and fourth. So we shade this second quadrant and the fourth quadrant. That's for tangent. Okay, therefore a theta that will satisfy both conditions must be in the overlapping quadrant, shaded in yellow and in green. So we know that theta is in quadrant 2, Q2. Let's see the second question. Again, try to shade quadrants that will satisfy this condition. The product of sine and cosine is positive. When the product of two things is positive, it is when both of them are positive or when both of them are negative. So we can shade when both of sine and cosine are positive. That happens in the first quadrant because all functions are positive. Cosine is positive in the fourth, sine is positive in the second. So these two quadrants are not good because it's only one of those functions positive. What about the third? Well, sine is negative in the third and cosine is also negative in the third. So we shade it. Okay, then the answer here is theta could be in quadrant 1 or quadrant 3. So there's two possibilities here. Knowing that tangent is given and it's equal √3/3 and sine is negative, find the exact value of secant theta. Well, first of all, I would suggest to translate secant in terms of cosine. It's 1 over cosine theta because it's a lot easier for us to remember properties of sine, cosine, tangent than the other three functions. So we can always translate it that way and figure out what cosine theta is in order to give the answer for secant theta. Now let's analyze the possible quadrants for theta. Since sine is negative, we will consider only quadrant 3 and 4 because that's where sine is negative. And tangent is positive because we have the value. So tangent positive is in the first and third. Therefore, our theta must be in the third quadrant. So theta is in quadrant 3. What does it mean? Well, if I will have a terminal here of my future theta and choose a point, the coordinates of such point will be both negative. So that's important piece of information. Now, tangent is the same as y over x. So y corresponds to √3, but it must be negative, and x corresponds to 3, but it must be negative because it's in the third quadrant. Okay, so I know what's y, what's x. I also need to find out r in order to find out cosine theta because cosine is defined by x over r. So from Pythagorean equation, it is square root of √3 square, which is 3, plus 3 square, which is 9. So altogether, this is square root of 12, which is the same as 2√3. Therefore, secant theta, which is equal 1 over cosine theta, equals 1 over, and cosine theta is x over r, so it's negative 3 over 2√3. But then we can take reciprocal, and we have negative 2√3 over 3 as a final answer. Let's try the second example. Knowing that cosecant is negative 2 and tangent is negative, find the exact value of cosine theta. Again, our goal will be to figure out what's x, y, and r of a point that is on the terminal of theta. Cosecant is negative 2 and cosecant is 1 over sine, so sine of theta must be reciprocal of negative 2, so it must be negative 1/2. Okay, so we know that sine is negative. We also know that tangent is negative. So in the system of coordinates, sine is negative in the bottom two quadrants, and tangent is negative in the fourth quadrant. So our theta is actually in the fourth quadrant. So the terminal is somewhere there. The theta is from here to there. The point will have coordinates first positive, second negative. Okay, let's try to list what's x, y, and r. Since sine is y over r, and r must be positive, so r must be 2, and y must be negative 1. Therefore, we can recover the x from Pythagorean equation. So x is the same as square root of r squared, which is 4, minus y squared, which is 1. So x is square root of 3. As soon as we have these three pieces of information, we can answer the question cosine theta equals x over r, so it's root 3 over 2, exact value. Another idea that will be very useful in finding values of trig function is a reference angle. We'll denote this as the name of the angle, usually theta, with the subindex reference, so theta reference. This is the positive acute angle formed by terminal side and x-axis. How does this work? If I have an angle 218 degrees and its terminal is in the third quadrant, then the acute angle from the terminal to the closest part of the x-axis, the shortest angle from the terminal to the horizontal line, that will be the reference angle. So in this case, to find out reference angle, we really go 218 minus 180, which is 38 degrees. That's the reference angle. In the second case, when the terminal is in the fourth quadrant, the closest path from the terminal to the x-axis is the angle 53. How do we find it? Well, this time the calculation is 360 minus 307. So that becomes 53 degrees. And another example, if the terminal is in the second quadrant, then the shortest pathway of the terminal towards the x-axis is this acute angle. So how to find this angle? Well, our original theta angle is actually negative this time, negative 240. So what we do is still subtract 180 in this case. So we calculate 240 minus 180. We're using the positive number 240 just because it's like a piece of fabric that you have this much and you cut off 180. So that gives us 60 degrees. I don't want you to try to memorize what to do, either to add 180, subtract 180, or subtract from 360. The best idea is just to look at the diagram and get the closest distance in terms of angle from the terminal to the x-axis. Always refer to the x-axis, never to the y. So let's find the reference angle for each of the given angles. 315. To figure it out, let's sketch quickly where the 315 could be. Well, it's more than 270, so it's somewhere in the fourth quadrant. Therefore, the reference angle is the remaining part. So theta reference in this case is 360 minus 315, which is 45. Next, we have angle in radians. So again, let's try to locate this angle. It's 7 pi 6. So it's more by pi 6 than 1 pi. It's pi plus another pi 6. Okay, that actually gives us the answer. This reference angle, the acute angle towards x-axis, is just pi 6. So theta reference equals pi 6. And let's try to do the next two by yourself. Stop the video and try to find out how much is that. In the case of 2 pi thirds, again located, 2 pi thirds is less than 1 pi, but more than pi half. So it's somewhere in the second quadrant. To find the reference angle, I need to find this piece. That means how much is pi minus 2 pi thirds. So theta reference equals pi minus 2 pi thirds. But pi by itself is 3/3 pi, minus 2/3 pi is just 1/3 pi, so it's pi thirds. And finally, negative 15 degrees. So that's somewhere in the fourth quadrant. The acute angle is just 15. Remember, the reference angle is always positive. So it's 15 degrees in this case.